Hello everyone, I am Yang Ai. My presentation title is Reverberation Modeling for Source-Filter-based Neural Vocoder. The contents include background, review of previous work, theory, experiments, and some demos. The background is that in the traditional speech synthesis method, we always consider the ideal situation that the speech is dry and clean, but in real-life applications, the audio signals captured typically contain room reverberation, and the reverberation poses a challenge to non-autoregressive neural vocoders, and the quality of synthesized speech usually degrades because there is no special module for reverberation modeling. Towards robust reverberation modeling for speech data, we propose a trainable reverberation module for neural vocoders. Based on the theory that a speech signal can be perfectly recovered by its amplitude spectrum and phase spectrum by short-time Fourier synthesis, this equation. So we propose the Hannet vocoder converts the acoustic features to waveform by predicting the amplitude and phase spectrum respectively. And the Hannet vocoder includes an amplitude spectral predictor ASP and a phase spectral predictor PSP. The ASP uses the acoustic features in the input and output the log amplitude spectral LAS. And the PSP uses the LAS and the F0 as input and output the phase spectrum. And the LAS and the phase spectrum use the short-time Fourier synthesis to get the final output waveform. And where the PSP is based on the neural source filter NSF model. The NSF model includes the source excitation module, neural filter module, and the condition module. And the source module uses the F0 as input and output the sine excitation signal. And the condition module propose the input LAS. And the neural filter uses the output of the source module and the condition module to predict the waveform. And the waveform uses the STFT to get the phase spectrum. In this paper, we first introduced the reverberation theory. A reverberated signal R can be calculated by convolving clean signal D with room impulse response IR-H localized this figure. And this is a time domain convolution operation. And we can at the same we can also use the frequency domain multiplication. That is the equation 2. And we add a reverberation module in the PSP of the Hannet. We only change the PSP in the Hannet vocoder. And the reverberation module is behind the original PSP module. It uses the dry waveform predicted by PSP as input and output the reverberated waveform. And the waveform uses the STFT to extract phase spectrum. And the key element of the reverberation module is how to predict the room impulse response. And we use two ways to predict the IR-H. One is the global time invariant IR, GTIR. The IR is shared for all the speech data, and the IR is regarded as a trainable variable in the network at the training stage. And another one is the utterance level variant IR. It is called UTV IR. For the same utterance, the IR is the same, but the different utterance occur different IR, and it is learned from the input areas by conditional neural networks. And for the training, this is the normal way of the training, which where we only have the reverberant waveform in the training set. So in this time, we can only define the loss function between the reverberant waveform predicted by the reverberation module and the natural reverberant waveform. And the loss function is the same as the original PSP. And this is the multitask training method. It is for a special situation where the natural drive waveform also exists. We can also define a loss function between the drive waveform predicted by PSP and the natural drive waveform. This is helpful for the learning of the original PSP module and the reverberation module separately, and the left one PSP module can learn the focus on generating the drive waveform, and the reverberation module can focus on how to recover the reverberation effect. And also, we can produce the drive phase spectra for some other applications, such as dereverberation. And this is our experiments. The dataset we use a multi-speaker reverberant speech database. The training set includes 11,012 utterances, and the validation set includes 560 utterances, and they include 28 speakers and 18 reverberation types. The test set includes 3 test scenarios, includes T1, 2 unseen speakers reverberation data with 6 unseen reverberation types. This is to test the generalizations of the model. T2 is 2 unseen speakers reverberant data with the same 8 reverberation types as in the training set. It is consistent with the training set. T3 is a dry speech version of T1. It is special for a reverberation task. The acoustic features include 80-dimensional mirror spectrogram, an F0, and voiced flag. The experiment models include NBR, the harmonic plus noise NS module without reverberation module. HBR, baseline high-net vocoder without reverberation module. HGTR is a high-net with GTR-based reverberation module integrated into PSP. HUTV is a high-net with a UTV-based reverberation module integrated into the PSP. HUTV-MT is the same as the HUTV but with a secondary task using drive waveform during training. And please first note that we use the P and the P drive to represent the reverberant waveform and the drive waveform predicted by PSP in the H system, respectively. First is the objective experiments. We use the T60 dimension errors for utterance with ground truth T60 equal to this second under test scenarios T1. And the T60 is used to measure the reverberation effect, and we use an open source toollet to bundle estimate T60 from the reverberant speech. And the T60 estimation error is equal to estimated T60 minus ground truth T60. This is the result. We use a box plot. We can see that the T60 estimation error is not error-free because bundle estimate the T60 from a speech is not error-free. And we first see this three system. We can see that the PGTI, PUTV, the PSP with the reverberation module can achieve better performance than the PSP without reverberation. That shows the reverberation module is effective. And by compare the PGTI, PUTV, we can see that the PSP with utterance variant reverberation, PUTV is better than PSP with global consistent reverberation PGTI. That shows the utterance variant reverberation is effective. And we then compare the P system, which is the PSP, the output waveform of PSP, and the H system, which is the output waveform from ASP and PSP. This is the full high-net models. It is obviously that the H system are better than the P system. That shows the ASP can also model the reverberant effect. And we then compare the high-net without reverberation in PSP and the ASL without the reverberation module. And we can see HBR is better than NBR. That shows high-net performs better than NSF, considering the reverberation effect recovery on this task. And we then conduct the subjective experiments. One is a similarity test on the reverberation effect. Score is from 1 to 9, and a higher score denoted a reverberation effect more similar to that in the natural reverberant audio tracks. Another one is the MUSHRA test on speech quality. Score is from 0 to 100, and a higher score denoted higher speech quality. This is the results of the similarity test. We use the box plot. We can see that the PGTI, PUTV, PUTV-MT, that is the PSP with the reverberation module, are all better than the PSP without reverberation, PBL. That shows the reverberation module is effective. And for test scenarios T1, the PSP with alternate variant reverberation PUTV is better than PIP with global consistent reverberation PGTI. But for test T scenarios T2, they are similar. That shows the alternate variant reverberation is effective for unknown reverberation type. That is the test scenarios T1. And then we then look at the PSP with alternate variant reverberation using multi-target training, that is the PUTV-MT. It achieves the highest score, and the PUTV-MT dry, that is the dry version of it, achieves the lowest score. That shows that the multi-target training is effective. And this result shows the conclusions on T3, test scenario T3, is the same as that on test scenario T1, and we will not introduce it in detail. And this is the MUSHRA test results. First, we can see that the high-net without reverberation in PSP, HBR, is better than NSF without reverberation. That shows the high-net performs better than NSF, considering the speech quality on this task. And this, we can see the HGTI, HUTV, HUTV-MT, that the high-net with the reverberation module in PSP are all better than the high-net without reverberation in PSP, that is HBR. That shows the reverberation module is effective on the improving the speech quality. And these results, we can see that HGTI, HUTV, and HUTV-MT, they achieve similar performance. That shows the alternate variant reverberation and multi-target training do not improve the perceived quality. And finally, let's listen to some demos. First, let's listen to the output waveform of PSPs. Please note that the quality of the waveforms is not good because it is just used to extract the phase spectrum, not the final waveform. Please only focus on the reverberation effect. This will list some explanation of the different modules. Let's listen to this one. Let's listen to the first 5 systems for saving time. This is a natural revert waveform.
6 spoons of fresh snow peas, 5 thick slabs of blue cheese, and maybe a snack for her brother Bob.
This is a PUTV-MT.
6 spoons of fresh snow peas, 5 thick slabs of blue cheese,
This is the PUTV. This is the PGTI. This is the PBL. Finally, let's listen to the output waveform of NSF and harness. We only listen to the test scenarios T1. This is a natural one.
Ask her to bring these things with her from the store.
This is a natural reverent speech. And then listen to the MBL results.
Ask her to bring these things with her from the store.
This is the result of the HBL.
Ask her to bring these things with her from the store.
This is the result of the HGTI.
Ask her to bring these things with her from the store.
This is the result of the HUTV.
Ask her to bring these things with her from the store.
This is the result of HUTV-MT.
Ask her to bring these things with her from the store.
Listen to more demos, please click on this URL. Thank you very much.